Hey, my name is Callie Chappelle, and thanks for tuning into this video about nerve conduction and currents. We'll get to it. So, before we do, here's a quick question for you. How does the body convert sensory information into an organized response? Through nerve signals. And nerve signals are moved throughout the body through nerve conduction. What's really cool is we can actually model this nerve conduction as circuits. So this is an interesting topic for me because it connects biology with electrical engineering, two of my great loves. So let's zoom in on a nerve cell known as a neuron. So neurons conduct the flow of sensory information throughout the body as electrical signals. And electrical signals are generated by the movement of ions or charged particles across a plasma membrane. Alright, so here's the structure of the neuron. And let's look at what happens when we are trying to move a signal down it. So the signal is first received here at the dendrites and moves to the cell body where the nucleus is housed. Now the stimuli is summed at the axon hillock until it becomes large enough to actually propagate down the axon. So the signal moves down the axon in what's known as the action potential and eventually reaches the axon terminals right here at the very end. Finally, neurotransmitters are moved across the axon terminal from the axon terminal to the dendrites of the next cell, across a tiny little space called a synapse. Now in this video, we're going to focus in on what happens here at the axon, but what happens at the synapse is also really, really cool. So let's take a look at a cross-section of the axon. So here's a cross-section, and here's cell membrane, and a couple of big things to notice. The first is the outside of the cell is net positive, and it's net positive because it has all of these positively charged sodium ions at a much higher concentration than elsewhere. The inside is net negative because there's a higher concentration of chlorine ions, among other things. But you'll notice that there are also positively charged things on the inside, and there are also negatively charged things on the outside. What matters is the overall charge in total. Finally, in the membrane, we have potassium channels, and we also have sodium channels. And these channels specially allow potassium to move through in this case, and sodium to move through in that case. Now, let's take a look again at the separation of charge, the net positive on the outside and the net negative on the inside. When we have separation of charge, it causes something called the electric potential, or in this case, what's called the membrane potential. An electric potential is measured in volts, and you've probably heard of volts before, and a volt and a 10-volt battery, or the volts coming out of a plug in your wall. And this just connects what we understand about the separation of charge and across the membrane to what we know about electrical engineering. So, and in particular, what happens in a capacitor. So here's a capacitor, pretty cool, and what is it? So we're going to talk about a parallel plate capacitor, which is just two metal plates that are connected to a battery by wires. So here's our battery, here's wires, and here's our capacitor, and let's figure out what's going on here. So a battery is just a device that separates charge. And I'm not going to go into the details of how a battery works here, but essentially you can think about positive charges moving from this end of the battery through this wire in the form of current to this side of the capacitor, and negative charges being pushed from this end of the battery, the negative end, through the wire and onto this side, this plate of the capacitor. So as the battery does its handy little job, positive charge accumulates on this side and negative charge accumulates on that side. And remember, it forms electric potential because electric potential is formed when we have a separation of charge. Well, now, Callie, you're probably asking me, this looks rather similar to what we just talked about regarding membranes, and you'd be absolutely right. So again, here's a simplified picture of what's going on across the membrane in a neuron. Outside the cell is net positive, inside the cell is net negative, and just like here at the capacitor, we have electric potential because of the separation of charge. So let's jump to understand how the nerve signal works, and then we'll talk about how we model it using capacitors. So the nerve signal is just an electrical signal, or remember, a movement of ions across the cell membrane. So here, ions are moving through a sodium channel, sodium ions, from the outside to the inside of the cell. And when ions move across, it changes the difference or separation of charge from the inside to the outside. And remember, it's that separation of charge that is the action potential. So let's think about how this happens, not just on a one-channel basis, but as it propagates all the way down the axon. And I like to think about this as people doing the wave at a sports game. So shout out to BuzzFeed Sports for providing this awesome GIF. And as you see, when you're doing the wave, when the person next to you raises up their arms, you raise up your arms, the person on the other side of you raises up their arms, and that's how the wave goes down a large audience like this. And it's the same thing with the action potential. So when the sodium channel, quote unquote, sitting next to me starts pumping sodium, then I start pumping sodium, the sodium channel on the other side of me starts pumping sodium, and that is how remember, the membrane potential, or the change in separation of charge, propagates down the axon in the form of the action potential. Really cool. So now let's take a look back to our circuit diagrams and connect what we just learned about the action potential moving down a neuron to what we know about capacitors. One more piece of crucial information though. If we have a weak signal, remember, if we have a weak signal at the action hillock, then we don't cause the neuron to fire. We don't cause the propagation of the membrane potential to go down the axon. What we do is we need some kind of way to make it stop. So here is a picture of how I've modeled what happens in a neuron in terms of circuit diagrams. So here's a switch, and when we close the switch, then it causes current to start flowing through this circuit. So closing the switch represents the stimulus reaching the axon hillock. So when the switch is closed, positive charges start being pumped by the battery this way until it reaches this resistor. And we have many different types of resistors here, but we know that the membrane provides resistance and the axon itself provides resistance, as well as this capacitor over here, which remember is the difference in potential across the membrane. So we can think about current like water flowing through a river. So as this current starts flowing from the battery and hits this resistor, it's kind of like water flowing through a river hitting river rapids. When the rapids provide resistance to the water, and it means that the water can't move as fast, the current can't move as fast through this resistance. And then the water keeps going, the current keeps going down this circuit until we reach the capacitor. The capacitor is kind of like a dam. Now, capacitors are pretty complicated, so this is a really, really basic understanding of a capacitor, but essentially it causes the buildup of charge, the buildup of water, and it slows down the flow of water, slows down the current afterwards. So, if we have many capacitors here in a row, this capacitor gets charged up kind of fast, charge accumulates on this capacitor kind of fast, but it's really slow here. This one takes a long time to charge, this one takes a really long time to charge, and so on and so on. So when we have a weak signal, the movement of the propagation of the signal down this circuit is really, really slow. But what happens when we have a strong signal and we want it to propagate really fast because we have a large enough signal to actually cause the neuron to fire? Well, that's like dumping a bunch of charge into the circuit. So we close the switch, we have a huge stimulus, and it's like dumping a huge amount of water into that river. It causes the dam to fill up much faster. And when the dam fills up, when the capacitor charges really quickly, it quickly reaches a threshold value which causes depolarization to happen. So here's a graph of the action potential. And depolarization is simply that phenomena that we just talked about, where sodium flows from the outside to the inside of an axon. So when depolarization occurs, it causes a change and a steady increase in the electric potential. It causes a large change in electric potential because the positive charges are moving from the outside to the inside. Okay, and this is what is represented by this graph. So the y-axis represents electric potential, which remember is just the separation of charge, and the x-axis is time. So as sodium flows in, we finally reach this top value where the cell's like, okay, that's enough, and it causes this thing called repolarization to happen. And repolarization is just where the cell's like, okay, let's rein it in, let's try to bring it back to to this initial value, which is called resting potential. So you normally think, well, wouldn't the cell just repump out these sodium ions? Well, actually, the cell devised a really clever way to do this, to repolarize the cell, by actually pumping out potassium ions. Now, potassium is also positively charged, so just like we pumped positively charged stuff in, we're going to pump it back out to bring it back down to resting potential. Now, one thing that's a little bit interesting about this is the fact that the cell actually hyperpolarizes, and that's because the cell actually pumps out too many potassiums. It actually goes past resting potential and goes quite a bit lower than that. And finally, the cell's like, okay, I goofed a little bit, and it returns back to resting potential. So this is what happens to a cell as the nerve signal propagates down the axon. It's represented by this graph. So I hope you found this video interesting. I think it's really cool that we can connect topics related to circuits to our understanding of biology, and hopefully accentuate our understanding of both. So take care, and peace, love, and science.